in this problem, this is truly a beautiful problem that similarly is not valid in other structure, I mean sets other than R. This is a typical beautiful result on real sequences. Okay, so what does it say? It says that if you have a real sequence, okay, let's be a sequence in R, so it's a real sequence, and what we want to show is, this is beautiful, that there exists, okay, let us prove that xn has a subsequence which is monotone. So either increasing or decreasing, not strict. I mean, it depends on if we put some conditions on the sequence, we can get a strict increase in sequence or strict decrease in sequence. This is also known in the literature as non-increasing, non-decreasing, increasing, and decreasing. So they don't use the word strict. But in any case, here we are dealing with large inequalities. And one way to see the difficulty with this problem, for example, is if you take, for example, the sequence. This is very interesting. If you take the sequence 0, 1, 0, 1, 0, 1, etc., periodic sequence with the values 1 and 0, so you will see that any monotone subsequence will be constant, either equal to 0 or 1. I mean, eventually constant, because you can start at 1 and then go down to 0, 0, 0, 0, okay? As well as starting at 0 and then you go 1, 1, 1, 1, 1. But eventually, the sequence will be constant. So how do we prove this? The way to understand this problem and have, because you can also use some fancy tools like the graph. You take a graph and you take two colors and you try to find an infinite path in the graph with the monochrome, with the same color, monocolor stuff. So there are some theorems that you can use to try to get the result that you want. But here we are going to use purely properties of the real line and the reals, okay? So one way to look at it is to go back to what is a sequence, okay, and how to see a sequence. Another way to see a sequence is you see it as a function. N gives you xn, okay? So, and of course you are going from the set of natural numbers to the set of R of real numbers, okay? So if you look at this as a function, then you have the graph of this sequence, right? And the graph will be on the positive parts. You start, for example, at 1 or 0, it doesn't matter, and you have these points, okay, and etc., etc., and you go like this, okay? So if you join them, okay, if you join the points, though I mean, of course, it's a discrete function, but if you join them, you get something like this, okay? And this is typical, for example, when you are dealing with the price of a stock market, when the data is collected discretely, okay? So this is not something that should be considered as like what's going on here. This has some very interesting many applications, and that's what in any case. So the idea here is, how do you find the subsequence which is increasing or decreasing? And one way to look at it, if you look what we call either a forward max peak or forward min, okay? Meaning, so these are points. So let's take another color here. So for example, if you look at this point here, okay? So, and you want to see, so there is a point here that is higher than it. So it's not a forward max. If you look at this point, this is a forward min. So it's lower than all the point that comes after it, okay? So we have this concept of forward min and forward max. How do we define that? So we'll say that n xn is a forward max, okay, if and only if it's the highest point for all the points on the graph coming after it. So for every m greater or equal than n, xn is greater than xm. Okay? And of course you have the same concept for forward min. Okay? So I will call them fm. Okay? So now let's look at so we have two cases. Either you have, so we have two cases. Okay, case one. So we have infinitely many forward. So we have infinitely many forward max points. So let's call them, for example, n1, x n1, n2, x n2, etc. with n1 less than n2, less than n3, less. So obviously, if you look at now the sequence, since it is forward, these are forward max points, then you are going to have obviously xn1 greater xn2 greater than xn3, etc. In other words, what you have here is a sequence xn which is decreasing, xnk, sorry, which is decreasing. So we found a subsequence which is decreasing. Okay? So that's the case that is easier. So the second case, case 2, okay, we have finitely many forward max point, which means that there exists an integer such that, okay, xn n xn is not a forward max point whenever n is greater than capital N. Okay? So what does that mean that we don't have forward max? Since if nxn is not a forward max, it means there exists, okay, so there exists k which is greater than n, in other words, a point that's going to be higher, okay, and such that xn is less than x k. Okay, so here it's easy by induction. Okay, by induction. Okay, we build, okay, a set of points n I x n I such that, okay, n1 is less than n2 is less than n3, etc. And x n1 less than x n2 less than x n3, etc. In other words, the sequence xni is a monotone increasing. So as you can see, in either cases, okay, so in conclusion, in either cases, we were able, xn has a monotone subsequence. Okay, now how this will help us prove the Bolzano-Weirerstrass theorem. So what does Bolzano-Weirerstrass theorem say? So we have BWT, Bolzano-Weirerstrass theorem. It says that any bounded sequence has a convergent subsequence. So we have to be very careful. It is a subsequence which is convergent. Okay. Now, if you look at the example I gave before, the 0, 1, 0, 1, 0, 1, 0, 1, that sequence is not convergent. It is bounded. Okay, but it's easy to come up with the subsequence which is convergent, either the constant sequence 0, 0, 0 or 1, 1, 1, 1. In any case, so this theorem is very profound because it tells you, for example, that closed and bounded subset of R are in fact compact. Okay, so it has many, many applications. When the Bolzano-Weirerstrass theorem was published or appeared, it gives them a beautiful structure of the topology of the real line. Okay, and it's very, very powerful in real analysis. In any case, so how do we prove this? The idea is that, okay, so if xn is bounded, okay, and x phi of n subsequence, any is any subsequence of xn, okay, then x phi n is also bounded. Now, what did we prove before? We proved that if xn is a real sequence, then there exists a subsequence x phi n which is monotone, either increasing or decreasing. So now what do we have? If xn is bounded, so now we know, putting everything together, that x phi n, there exists x phi n, okay, which is both monotone and bounded. And now we use the fact that a monotone bounded sequence is convergent, and therefore x phi n is convergent. Okay, so keep in mind, just for the sake of, if recall, okay, that if xn is monotone increasing and bounded above, then xn is convergent and its limit is the sup of the xn's. Also, we have a similar, of course, number 2, we have a similar result for monotone decreasing and bounded below. So the limit will be, it's convergent, and the limit will be the infimo.